In this session, we will talk about standard turning holders. Standard turning holders are the tools that hold standard turning inserts, and the holders are clamped inside a turning machine. Here on the left, you can see inside a CNC turning machine equipped with different holders clamped to a turret. In the middle, you can see a holder for VBMT. By saying VBMT, I mean an insert whose code's first four components are VBMT. You can go back to the standard turning inserts section of this course if you don't know about the rules of turning insert coding or if you've forgotten them. Now back to holders. The holder in the middle is an external holder. An external holder means a holder that is mainly used to machine external surfaces of a workpiece. In contrast, the holder on the left is an internal holder, mainly used to machine internal surfaces or inside a hole or bore. Usually, external holders have a rectangular cross-section, while internal holders have a circular cross-section. First, I will discuss the coding rules for external holders. As I said before, an external holder is mainly used to machine external surfaces of a workpiece. As an example, you can see an external holder in this picture. Now you can see an example of a holder code in millimeters, and the first one is in inches. The second one. I have named each portion of a millimeter holder code by a number from 1 to 9, and for an inch holder by a letter from A to I. There is a reason why I did not use numbers for both, and I will discuss that later on. For both millimeter and inch coding, the first portion of the code, I mean 1 and A, represents the way the insert is fixed to the holder. Different letters are used to represent the fixation method, and you will see some examples of the most common ones. If the first portion of a holder code starts with S, then a screw is used to fix the insert over the holder. As you can see here on the right picture, the first letter of the holder code, which is inscribed on the body of the holder, starts with S. And on the left, you can see that a screw is used to attach the insert to the same holder. Usually, the screw clamp, which is represented by S in the holder code, is considered a weak clamping method and is used for positive inserts. By positive inserts, I mean inserts where the clearance angle is not 0. If you don't know or don't remember what an insert clearance angle is, I recommend you check the standard turning inserts section of this tutorial again. Although the screw clamping is weaker in comparison to other clamping methods, it is very compact and provides accessibility. Therefore, it is mainly used for positive inserts, internal or boring machining, and for operations that do not generate much cutting force. Another way of fixing an insert is called rigid clamping, represented by D in a holder code. As you can see, the holder clamp has a pin that goes inside the insert hole, and by pushing the insert downwards, it fixes the insert in its place. The middle picture shows the holder code inscribed on the body of the holder, starting with D. Rigid clamping is stronger than screw clamping. However, it is bulky and not as suitable for internal machining or boring. Holders used for roughing or operations that generate high cutting forces have a component called a shim, where the insert sits over the shim made of hard material. Shims help distribute force and extend the life of the holders. Shims are replaceable components, and if they are damaged, they can be easily replaced. Another example of clamping is called a top wedge lock, represented by M. As you can see, the holder has a top clamp and a center pin that goes through the insert's hole. Both the center pin and the top clamp are used to hold the insert in place. There are some other clamping methods, such as lever lock, represented by P. There are also other clamping methods specific to certain holder manufacturers. The second portion of a holder code, I mean 2 and B, represents the insert shape, and its coding rule is the same as for inserts. For example, C is used to represent a rhombus with an 80-degree angle, and a rhombus with a 55-degree angle is represented by D. You should pay attention to the second character of a holder code and the first character of an insert code. They should be the same if you want to use them together. I will explain this more clearly. For example, if an insert is a rhombus with an 80-degree angle, its first code will be C. You can use this insert with a holder where the insert pocket is made for rhombus inserts with an 80-degree angle. This means that the holder's second code character should also be C, the same as the first character of the insert. There are some other characters that should match if you want to use an insert with a specific holder, which I will explain later. The third portion of a holder code, 3 and C, represents the holder's lead or approach angle. As you can see in the left picture, the lead or approach angle is the angle between the cutting edge and the part, which in this case is about 93 degrees. Based on the standard, different angles are represented by different characters, as shown in the table. According to the standard, if the lead angle is 93 degrees, the symbol for it is J. Therefore, the third character of the holder code, which is inscribed on the holder body, is J. The fourth portion of a holder code, 4 and D, represents the matching insert clearance angle. Here you can see two sample codes for holders. The first one is based on the millimeter or ISO standard, and the second one is based on inches. As I said before, I have named each portion of the code by a number from 1 to 9 for millimeter coding and by a letter from A to I for inch coding. Again, I should mention that this naming with 1 to 9 and A to I is something I have done for the purpose of this course, so I can refer to different portions of the code. It is not related to or mentioned in the standard. Now back to the fourth portion of an external holder, or portion 4 and D. As I said, it represents the clearance angle of the matching insert. If you remember from the standard turning inserts section of this course, it can be represented by a character based on the insert clearance angle size. It can be represented by different characters such as P, C, B, and N. P is for 11 degrees, C is for 7 degrees, B for 5 degrees, and N for 0 degrees. Again, the fourth portion of an external holder should represent the clearance angle of the matching insert. You can see in these sample codes of a holder and matching insert that the portion representing the clearance angle is the same. They are highlighted in blue and both are N. This means that you cannot use an insert with a clearance angle of 7 degrees with a holder designed for an insert with a clearance angle of 5 or 0 degrees. The fifth portion of a holder code is called the hand of the tool. If you hold the holder in a way that the insert is towards you and the insert is tilted to the left, the hand of the tool is represented by L. If it is oriented to the right, it is represented by R, as shown here. For CNC lathes, left-hand holders are used 70 to 80% of the time, but there can be CNC lathes using right-hand holders. The sixth and seventh portions of a holder code represent the dimensions of a holder's cross-section. The sixth portion represents the height, and the seventh portion represents the width of the holder's cross-section. Now, for the eighth and ninth portions, there is a difference between millimeter and inch coding. For millimeter coding, the eighth portion represents the length of the holder, the blue circle, and the ninth portion represents the matching insert size, the black circle. In inch coding, this is reversed. The eighth portion represents the insert size, and the ninth portion represents the holder size. That is why I used 1 to 9 for naming millimeter holder portions and A to H for inch coding. Again, this naming is just for the purpose of this course, so I can refer to different portions of a code, and it is not related to or mentioned in any standard. As I said, the eighth portion of a holder code in millimeter coding represents the length of the holder, while in inch coding it is the ninth portion. Here you can see a table to find the symbol that represents the holder length. Section 9 and H of a holder code represent the matching insert size. Here, you can see a holder and matching insert code. As you can see, they have the same insert size symbol. You can go back to the standard turning inserts section of this course if you do not know about the turning insert size or if you have forgotten it. Let me know if you'd like to format it differently or need anything else. Now it is time to discuss internal holders. Internal holders or boring bars are mainly used to machine internal surfaces or the inside of a hole or bore, and they usually have a circular cross-section, while external holders have a rectangular one. Here you can see a picture of an internal holder or boring bar and its code. I will not go through each segment of the code in detail, because most of them are similar to external holders. The first segment of an internal holder code describes the type of boring bar shank, for example, whether it is steel, carbide, or coolant through or not. Accordingly, a symbol is used. Here I should explain a bit about coolant through and what it means. Some boring bars have holes through them, which can be used to deliver coolant onto the insert. This might help in evacuating chips from the bore, but on the other hand, holders with through holes are weaker and more susceptible to vibration compared to holders without through holes. Carbide shanks are more expensive than steel shanks, but they are more rigid and deflect or vibrate less. Therefore, you can get better tolerances with carbide shanks. Now back to our sample boring bar. Its shank is steel without coolant ducts, so its code starts with S. The second segment of an internal holder code describes the boring bar shank diameter. Obviously, if the shank diameter is bigger, it is more robust and less prone to vibration. On the other hand, the maximum diameter of a boring bar that you can use for an operation is limited by the diameter of the hole or bore. For example, if a bore or hole diameter is 50 millimeters, you obviously cannot use a boring bar with a diameter of 70 millimeters. Generally, vibration and deflection of boring bars are the main problems that can occur during internal machining. Therefore, positive inserts are usually used in internal machining to reduce machining forces. Also, try to use boring bars with the largest possible diameters, as they are more robust and resist vibration and deformation. Let me know if you'd like it in a specific format or need anything else. Other segments of an internal holder code are similar to external holders, just in a different position in the code. The third segment of an internal holder code describes the boring bar length. It is similar to external holders, and in our sample code, the length of the holder is 180 millimeters. Therefore, it is represented by Q. The fourth segment of an internal holder describes the method by which the insert is fixed over the holder. This is a repetition of what we had for external holders. In our sample code, the insert is fixed over the holder by a screw. Therefore, in the code, we have S. I will describe other segments faster because they are a repeat of what we had for external holders, and I described them in detail there. The fifth segment of an internal holder describes the insert shape. In our sample code, it is triangular, so it is represented by T. The sixth segment of an internal holder represents the lead or approach angle of the holder. The seventh portion of the code describes the clearance angle of the insert. The eighth segment describes the hand of the holder, meaning whether the holder is right hand or left hand. And finally, the last portion represents the insert size. As I said before, these segments are the same for external holders, and I explained them in detail earlier. In this session, I covered standard turning holders, both internal and external. In the next session, we will discuss turning operation cutting data.